C1 cosine, and this is the imaginary part of this number. It's going to be omega 1t plus C2 sine omega 1t. All right, so it's kind of interesting. We got a comment when it was undamped altogether. We got something of this form, except we had a different period, right? When it was which one? I'm forgetting. When it's over damped, we just got e terms. Okay. When it's under damped, or no, what was it? Critically damped. Oh, critically damped, we got the two e terms. And when it's under damped, we get both. An e term, e factor, and the cosine and sine. Okay. So notice here a couple things. We got this e to the a negative power. So as t goes to infinity, no matter what this oscillation does, this is going to have a constant amplitude. But this drives it down to 0. But it will still oscillate. Okay. So while we got our books open, let's look over. So they give you on that same page 191. They give us a couple pictures of the overdamped, critically damped. It could cross 0, right? And then on the next page, we have the one where it's under damped. Okay? And we get this thing that's a combination of a periodic function, sine function, sinusoidal, bounded by this pure exponential. So what happens with the form of our equation? It was cosine omega 1t plus sine omega 1t. This acts as a dampening, it takes the amplitude. It's like a variable amplitude. So if you graph that by itself, e to the negative pt, you see that top bound. That's just a pure exponential function. If you see its opposite, negative e to the negative pt, you see the lower bound. Okay, and this function bounces back and forth between them. So it's like a squeeze theorem problem, really. What happens is at the bounds, the e to the negative pt and negative e to the negative pt are eventually going to 0, and that function in there is just oscillating but bouncing back and forth between them. So that's why it's underdamped. It still oscillates. That damping force is not so strong, so it still oscillates but with smaller and smaller amplitude over time. Okay. That's the coolest one. It's nice, nicest picture. Okay, we'll do one example and then we're going to take a break because we need it. So the book makes a note that, this is not a periodic, the blue one. That's not a periodic function because it doesn't repeat the exact same thing over and over. It has that dampening, that reduced variable amplitude. Okay, so it's not a periodic function. So we wouldn't talk about the period of that function. They talk about what's called the pseudo period. Okay, and you could take that to be the time in between the absolute minimum or the local minimums, right? So it vibrates. It goes out to say the left one time. The next time over, it doesn't go as far. Next time, it doesn't go as far. But you could talk about the time between those, maximum deviations from equilibrium, and that's what's called the pseudo period of the oscillation.
Is that time going to be the same in between, or the frequency? Yes.
Yeah.
In fact, in proportion with the speed.
Yeah. I'm not going to write it on our notes, but in fact, this turns out to be the pseudo period.
So it's not considered an amplitude if you define it as a function?
What's that?
A changing amplitude is not really an amplitude. You can't just define the amplitude as a function of e to the negative pt.
No, it's a sort of variable amplitude.
Okay.
Yeah. So in trig, last time it's been a while since I've taught trig, but just testing their knowledge of periodic function, I would do something like that. Say, is that periodic? You can change that. You know, if I do cosine t or whatever it is, cosine beta t, that's going to be periodic. But any constant out here would also make it periodic. That would be a constant amplitude. If you build some function out here like 1 plus 3x, then you can think of that as a variable amplitude. And what it's going to be doing is the line, or yeah, 1 plus 3x looks something like this, based on the scale of the graph. The cosine function, cosine is 0, you get 1. Cosine is going to do something like this, right? So this function would do something like that. So it would take that amplitude and, oh no, wait, no, that's a midline. That's a midline.
It's gonna,
Right,
it's
right,
gonna
right,
hit the top
right,
of
It'll
it.
just get bigger oscillations.
Right,
Yeah.
X is 0, it goes like this, yeah. Sorry. There's 1 plus 3x, there's its partner, opposite, -1, because cosine can bounce back and forth between -1 and 1. So this function would do something more like this.
Okay.
The amplitude, sorry, I had a midline. I changed the midline. I had a variable midline. But this would be a variable amplitude. The amplitude on one end would be 1 plus 3x. This function would be -1 minus 3x, because as cosine bounces back and forth between -1 and 1, it will just be 1 plus 3x, or its opposite. So that's building in a variable amplitude. Of course, this would be something where the amplitude is getting larger and larger and larger. Chaos, right? Whereas here, the amplitude is dampening towards 0. Yeah, resonance. Okay. All right. So one example, and we're going to do one of your homework problems. So pay close attention. So those are all the cases that we're going to do. Our example, we're going to do one from the homework list, page 197, number 24. Okay, so number 24 says, it's going to be not a proof so much, but show that this is true. So if you have a critically damped spring dash pot system, show that the position function can be written this way. So we're just basically deriving the function where they define x of 0 to be x naught, so some real number, and x prime of 0 to be v naught, which represents the initial velocity of that vibrating mass. Okay? So they're just asking us basically to derive this. So it's just a bit of algebra mainly. And of course, knowing what the form of the critically damped position function is. Okay, so we're starting with some assumptions. Not assumptions, but just some terminology. X of 0 is x naught. X prime of 0 equals v naught. And the overdamped case, and you're not going to, don't memorize these.
I would say critically damped, didn't it?
Did it say, oh, critically damped, right. So critically damped is when it's equal to 0, right, we get the repeated root form. Okay. So critically damped case, the position function will be e to the negative pt c1 plus c2t. We got that repeated root, and so we picked up a linear factor in the general solution. Okay. All right. So we got some things to figure out. Now, first initial condition, they tell us that x of 0, we're just calling that x naught. It's a number, it's a real value, it's just we don't know. We're taking that to be a parameter. But x of 0, if we plug it into this function, right, 0 is in for t, that's our independent variable. So put 0 in for t, and what do we get? I get e to the 0, that's 1. C1 plus C2, 0, so that's 0. And they're telling us that we're just calling this value x naught. Okay, good. So this gives us right off the bat that our unknown coefficient C1 just represents the initial position of that. Okay. All right. The other initial condition, well, we'll take care of that in a second. I first need to find a derivative of this because the other initial condition involves x prime. So let's find x prime of t. Product rule, derivative of the first times the second. I can view this as a product of two separate functions. So derivative of the first, I get negative, oh right, negative p is going to pop out. Negative p e to the negative pt. So derivative of the first times the second, plus the first, that's e to the negative pt, times the derivative of the second. What's the derivative of this? Just c2. Okay. So the other initial condition was that x prime of 0 equals v naught. So let's put in 0 for t. So e to the 0 will be 1. I'll have negative p times 1. C1 plus C2 times 0, so that's just C1 there. Plus, and putting in 0 into this t gives me 1, and that's just C2. And they're telling us that x prime of 0, we're calling that v naught. Okay? And C1 is x naught. So I get negative, oops, yeah. So we get negative p times, and we just solved for C1, that was x naught, plus C2 equals v naught. So solving this for C2, in terms of everything else, gives us v naught plus px naught. All right, let's just use this bit of space here. So, position function is x of t equals e to the negative pt, c1 plus c2t. C1 is just x naught, plus c2t. C2 is v naught plus px naught times t. Now, is that what were we asked to show?
Show that it's exactly that.
Right. I don't know. Is that exactly it?
Yep.
Yeah, I'm going to put the e to the pt over the other side and expand this. We got x naught plus distributed t, v naught t, plus px naught t, e to the negative pt.
You move to the left.
Sorry. X naught plus v naught t plus px naught t, all times e to the negative pt. So that one was just a manipulation and solving for those constants, c1 and c2. Okay. In terms of these parameter values, if I knew, so this is nice. You use this probably. If you know that you're in a critically damped case and they give you the initial position and the initial velocity, we can write down the whole function. As long as I find what p is, p was, 2p was equal to k over n or something like that. All day, just parameters running around in my head. So there's a question?
Oh, no, just stretching.
Okay. All right, let's take a break. Let's take 12 minutes or so.